Hello everyone, today we're going to talk about frequency transformations in multiple dimensions. The prerequisites for this material are calculus, linear algebra, Fourier series, the sampling theorem, and the discrete Fourier transform. We're going to consider multidimensional signals, which we're going to model as functions that are square integrable and are defined on a hyperrectangle in RD. So for example, in 2 dimensions, what I mean is, if this is the 2D plane, we're going to consider functions that are between a1 and a2 and b1 and b2. Okay? So they're defined on this rectangle here. Okay, that's what I mean. The inner product between these functions is just the product integrated over this hyperrectangle where they are defined. Notice that we take the complex conjugate of the second one because we're going to be working with complex functions, basically because we want to use complex exponentials, as we will see in a moment. The reason why we need these things to be square integrable is that when we look at the norm of a signal, the norm is going to be defined as the inner product of this signal with itself. So this is just the integral of the square, and that has to be finite. Okay, so that's the reason why we're considering square integrable functions. The goal here is to extend frequency representations that we learned from one dimension, such as the Fourier series and the discrete Fourier transform, to the multidimensional setting. In particular, we're going to be interested in trying to express signals in terms of multidimensional sinusoids. So what is a multidimensional sinusoid? It looks very much like a one-dimensional sinusoid. It has a certain amplitude, it has a certain phase. But now the main difference is that here, instead of having a product between two numbers, a frequency and a time index, we have an inner product between two d-dimensional vectors. Now, the multidimensional extension of the frequency is d-dimensional. In order to see what this means and what kind of functions we obtain with this formula, let's see what happens when we move t in different directions. Okay, so if we move t in a direction that is orthogonal to f, then it turns out that the function does not change at all. The function is actually constant in any hyperplane that is orthogonal to f. Why? Because when we expand this inner product, we obtain the inner product between f and v, and that's just 0, because this is how we're defining v, so that the function stays exactly the same. If we move in a direction aligned with f, okay, and the unit norm in the direction aligned with f is just this, okay, so if we move in the direction of f divided by its L2 norm, which is just a unit norm vector in the direction of the frequency, then the function is periodic with period 1 over the norm of the frequency. How do we see this? Well, we move in that direction weighted by 1 over the norm. This is just equal to the inner product. So this second term is the inner product between f and itself, so which is just equal to the L2 norm of f squared. So this is going to cancel out with the denominator, and we're going to have that this just produces a shift of 2 pi, and because the cosine is periodic with period 2 pi, this leaves the function exactly the same. So this tells us that if we move in the direction of f, we're periodic with period 1 over the norm of f. So f is telling us two very important pieces of information. First, in what direction is the function periodic? And second, how rapidly does it fluctuate? Okay, because if we increase f, the period diminishes and the fluctuations become more rapid, more quick. So let's see. We're going to take a look at a couple of pictures. So here, what I was saying is, here this produces a shift by 2 pi, and then that disappears because the cosine is periodic with period 2 pi. Just to make sure that was clear. So now let's take a look at the picture. So here, f is the vector 0, 5. And here we're plotting the function with respect to t1 and t2. So f basically points in this direction. And you can immediately see that in directions that are perpendicular, orthogonal to f, the function remains constant. Okay, so we have a planar wave that moves in the direction of f, and it is periodic in that direction, as you can see. Now here f is equal to 10, 0, so it's pointing upwards. Again, orthogonal, when we move orthogonal to f, this is f, when we move orthogonal to f, things are constant, and in the direction of f, things are periodic. And the period is inversely proportional to the norm of f, so here we see a higher frequency, the shorter period, than here. Here the period is longer because f, the norm of f is smaller. F does not necessarily have to be aligned with the axis, it can be aligned in this way. So here the vector is 3, 4, and again, perpendicular to f, we are constant. Here this is yet another orientation. Here f is in this direction. And you can see that here the norm of this vector is larger than the norm of this vector. So as a result, here the period is larger than here. Here this is a higher frequency to the sinusoid. Okay, when we're dealing with 2D sinusoids, we have the same problem that we did when we're dealing with 1D sinusoids, which is that we have this phase parameter that essentially just shifts the sinusoid in the direction of f, and we don't want to have to include it in our basis of functions that we're going to use to decompose signals. In order to avoid that, we can just use complex exponentials as opposed to just real sinusoids. Complex exponential has a real part that is a cosine, which is the multidimensional cosine that we just defined, and the imaginary part is a shifted cosine, which is a sine, again similar to what we have just defined. And now the trick here is that if we have any arbitrary phase, theta, we can express it in terms of two complex exponentials. The reason is, I'm just going to remind you very quickly, although we already saw this for 1D, that the complex exponential is equal to cosine plus I times sine. If we look at the complex exponential of minus ix, it's equal to cosine of minus x plus I sine of minus x. But now cosine of minus x is just cosine of x, and sine of minus x is minus sine of x. So now this, when we sum these guys up, the cosines disappear and we just are left with, the sines disappear and we're left with the cosines. Okay, so this is why this equality holds. And now because we have the exponential of this sum, we can separate it, we can factor it into the product of the exponentials, and the phase comes out as a complex coefficient, and we have two basis functions that do not have any phase dependence, which is great because now we can express any multidimensional sinusoid, real sinusoid with any phase, as a linear combination of just two basis functions. It's exactly the same idea as in one dimension. It turns out that multidimensional complex sinusoids can be expressed in terms of 1D complex sinusoids or 1D complex exponentials, because we can express the inner product as this sum. And now we can just split the exponential, the exponential of the sum into the product of the exponentials, and each of these terms is just a complex sinusoid in itself, where the frequency is equal to the corresponding entry of the frequency, and the time index just corresponds to the corresponding entry of the time index. So now from now on, we're going to focus on two dimensions. The frequency will have two entries. This is two-dimensional vector. The time index will have two entries. These are, we already took a look at some 2D examples a moment ago when we were describing the multidimensional real sinusoids. So now when we consider a complex sinusoid in 2 dimensions, we can express it as just a product of two one-dimensional sinusoids that would be aligned in the direction of each of the axes. So now, as in the case of, as in 1D, we're going to define a family of complex sinusoids that have frequencies that are integers. So this, if you remember, we had integers divided by the length of the interval where the function is defined. So now, instead of an interval, we have a square. So we're going to consider functions that are restricted to a square that is t by t, and the frequencies, just to give you an idea, they're integer multiples of 1 over t, right? So for k equals 0, we're going to have constant sinusoids, but k equal 1 is going to basically look like this in this direction and like this in this direction. Of course, I'm only drawing the real part. If we have k equal 2, then this is going to fluctuate twice in this direction. And realize that you can also combine k1 equals 1, k2 equals 2, and so on to get different 2D sinusoids. Again, we already looked at how 2D sinusoids look. Now we're going to here show them in terms of complex sinusoids. So we already, what I meant is, I said that in a bit of a confusing way. We already looked at real 2D sinusoids. Now we're going to look at how they are formed by combining two complex sinusoids, so that we understand the connection between this complex family of complex sinusoids and those examples that we already saw. Okay, so we had one in which the frequency was 0.5. The way we do that is canceling, using 0.5 and 0 minus 5. And that is what yields this cosine function that we saw before. Okay. Here the phase is 0. Same thing here. We have these two frequencies. Of course, the frequency is always divided by t, but in this case, t is just equal to 1. Okay, we are in the, so realize this is t and this is t. Okay. So these two frequencies here produce this sinusoid here, which combines the complex exponential with frequency 10, 0 and minus 10, 0. Okay. Same here with 3, 4 and minus 3, minus 4. Same here with 8, minus 6 and minus 8, 6. Okay. So this is how the real sinusoids that we saw before are formed as linear combinations of complex exponentials or complex sinusoids. So it turns out that this family of complex sinusoids where k1 and k2 are integers and the frequencies are given by k1 over t in one direction and k2 over t in the other direction. So the frequency is actually k1t, a vector that has entries k1 over t and k2 over t. In that case, these are an orthogonal set of functions on the interval on this rectangle 0t, 0t. Okay, this might not be too surprising because we know that in one dimension each of them are orthogonal basis functions for the interval 0t. But let's prove this. Okay, we have that we can write the 2D complex exponential as a product of 1D complex exponentials. When we expand the product of the 2D complex exponentials, we have this for the first one and this for the second one. And now we can just group terms and move the integrals around so that this is just equal to the inner product of the first 1D complex exponential of each of them times the inner product of the second 1D complex exponential of each of them. Because we know that the 1D complex exponentials are an orthogonal family, this and this is only going to be non-zero if k1 is equal to j1 and k2 is equal to j2. Again, we proved this in the video on Fourier series. These continuous complex exponentials, continuous complex sinusoids, are an orthogonal family when we consider frequencies that are k over t, so some integer divided by t, and they're restricted to the interval 0t, which is the case here for these 1D components. So this is going to be 0 as long as they're not the same. If they happen to be the same, then what happens is that each of these guys, if you remember, is equal to t, so we get t squared here. Okay, and you can check the 1D. I mean, it's easy to show, but you can check the video on 1D sinusoids or the notes for that. So the norm of the 2D sinusoids is equal to t. And they do form an orthogonal family, which is great in order to build a representation based on them. And that representation is the 2D Fourier series, which is defined almost the same as in 1D. We basically have Fourier coefficients that are indexed by k1 and k2, and they are obtained by taking the inner product with the corresponding 2D complex exponential or complex sinusoid, which is obtained by just taking this integral. When we want to reconstruct the signal from these functions, basically we sum over k1 and k2, and we weight each of the 2D sinusoids or 2D complex exponentials by the corresponding Fourier coefficient. Just this is essentially the same as in one dimension. The only difference is that now we're building the function using 2D sinusoids as opposed to 1D sinusoids. Okay, now I'm going to show you an example where 2D Fourier series is really, really important, and that's magnetic resonance imaging. This is a non-invasive medical imaging technique which is found all over the place. You might even have had one. This imaging technique works by measuring responses of atomic nuclei in biological tissues at high frequency responses to high frequency radio waves when the biological tissue is placed in a super strong magnetic field. So they require having these extremely strong magnets, which makes it a little bit expensive. The radio waves that you send into the body in order to be able to measure these magnetic responses are adjusted so that each measurement equals the 2D Fourier coefficients of the proton density of hydrogen atoms in a region of interest. For example, you might be interested in looking at a slice of your knee. So by looking at the density of protons in hydrogen atoms in water, you get a picture like this, which essentially tells you, the structure of the tissue, which is super useful for many medical applications. But interestingly, you don't get to see this. What you get to see are the Fourier coefficients, and here I'm showing you the magnitude of the Fourier coefficients, because remember that these are complex numbers, so there is an associated phase. But just to be clear, these are different frequencies. So at any point here, like here, this corresponds to, so if you go here, this Fourier coefficient has a certain value, corresponds to a frequency of -1, -1. Okay, you go here, would be 2, 2, and so on and so forth. Okay, so each of these entries in this heat map tells you the magnitude of the corresponding 2D Fourier coefficient. When we build the Fourier series corresponding to this, boom, we get a slice of your knee, which is pretty amazing, I have to say. I'm always amazed that this actually works. Okay, so now let's think about what this means in terms of how would this be affected if you get just a subset of the Fourier coefficients. So I want you to think about what happens here if we take frequencies only up to here and up to here. Okay, so we only take these frequencies and put everything else to 0, and we reconstruct the signal just like that. Is this going to look higher resolution or lower resolution? I would like you to think about this before, so you can pause the video. So it's going to be significantly lower resolution. Now think about what's going to happen if we take high frequencies up to here, but we truncate the Fourier series in this direction, so we don't take these coefficients. This means that we're using very high frequencies in this direction, but only low frequencies in this direction. So think about how this is going to affect things. Okay, so this is what happens. We are very blurry when we look in this direction, you know, this slices like this is very low resolution. But in like vertically, we get better resolution, which doesn't help us very much because here the details are mostly in this other direction. Okay, so here now we're going to see a big difference because now we're going to get better resolution in this direction. And we're going to see that actually that makes a huge difference. Okay, like we see, for example, here, these details, because we are getting high resolution in this direction, whereas those details here were gone. Having high resolution in this direction actually doesn't help us very much. Okay. Anyways, this is just so that you realize that in contrast with 1D, here there is, there are choices to make in terms of getting Fourier coefficients, like more Fourier coefficients in one direction as opposed to the other, and it can make a big difference to the image quality. Of course, we want to get as much resolution in every possible direction, and then we get a very nice looking knee. Being able to reconstruct MRI images with a small number of coefficients is actually very important because, roughly speaking, the more resolution you get in the Fourier domain, the longer you have to stay in the machine. So the measurements take longer time. So it's a very important problem, how to reduce the number of coefficients that you take while preserving image quality. Okay, so now we're going to define band-limited signals in a very similar way to how we define them in one dimension. Again, we're in this rectangle 0t times 0t, and we say that a signal is band-limited with cutoff frequency kc if we take our Fourier coefficients between minus kc and kc. So the picture would be something like this. Okay, so here I went a bit crazy with my annotations, but basically the idea is that here we would be between minus kc and kc, and here also the same. Okay, my kc and minus kc. Okay, so essentially now the signal depends only on a finite number of parameters, which has this kc squared Fourier coefficients, and we can actually recover them from equispaced samples, essentially like we did in one dimension. So here this is a matrix of samples. So just to be clear, we have this square and we're sampling on an equispaced grid, okay, where we're taking n squared measurements. The sampling theorem in 2D tells us that if n is greater than 2kc plus 1, realize that we're taking n squared measurements. In 1D, we're taking n measurements. So here we're taking n squared measurements, which makes sense because we have kc squared parameters now. Okay, actually, not kc squared, 2kc plus 1 squared parameters, right? Because realize that here there's 2kc plus 1 terms in each of these sums. So the total number of parameters is 2kc plus 1 times 2kc plus 1. So it stands to reason that you need at least those number of samples. Okay, that's known as the Nyquist rate, just like in 1D. Okay, so notice that we're representing the samples as matrices, and we're going to think of these matrices as vectors, where the standard inner product is basically the same as taking the dot product between the vectorized matrix. A vectorized matrix just contains all the entries within one vector. You can also write this inner product as the trace of the adjoint of one matrix times the second matrix. Okay, but you can just think of this as you could just put all of the entries of the matrix, of this matrix, for example, into a very long vector of dimension n squared, and the inner product that we have defined here is the same as the normal scale, like the normal Euclidean inner product between n squared dimensional vectors. Okay, why am I telling you this story? Because now we're going to define a 2D discrete sinusoid, which is what you obtain when you sample 2D continuous sinusoids. The analogy with 1D is direct, because here we have a product between these two discrete sinusoids that we had defined in 1D. Notice that this basically means that you have this 1D discrete sinusoid in one direction, and you take the outer product with the other discrete sinusoid. This gives you a matrix like that, and that's your 2D discrete sinusoid. So it turns out that when we sample the continuous, the continuous 2D sinusoid K1, K2, we get the discrete sinusoid. Again, we have this issue where many continuous sinusoids are going to be mapped to the same discrete sinusoid. This is exactly the same as what happened in 1D. And you can see this directly because anyways, they are products of the 1D continuous sinusoids that get mapped to the 1D discrete sinusoids. So it just stands to reason that this aliasing problem that we had in 1D is going to happen here too. This is why we need the condition that n has to be greater or equal to 2 times the cutoff frequency plus 1. Okay, so these discrete sinusoids, just building upon the results that we established in one dimension, form an orthonormal basis. This is very easy to prove because when we consider the inner product between them, we can basically express the inner product between them as just the inner product between the 1D discrete sinusoids, and those we know are orthogonal because of what we proved in the 1D case. So this is equal to 0 unless K1 is equal to K2 and K1 is equal to L1 and K2 is equal to L2. I'm going a little bit quickly over this, but basically the idea is that because this 2D discrete sinusoids are just the outer product between the 1D discrete sinusoids and those are orthogonal, then this directly implies that the 2D discrete sinusoids form also an orthogonal family. As a result, we can prove the Nyquist theorem based on these 2D sinusoids, and the way we recover, so basically, let me go slowly through this. We have a bandlimited signal x, okay, which is defined on this rectangle 0t by this square 0t by 0t, and there's a cutoff frequency kc, so we can recover this 2kc plus 1 squared. So the number of Fourier coefficients is 2kc plus 1 squared. We can recover those coefficients by taking inner products with the corresponding 2D discrete sinusoid as long as n is greater than 2kc plus 1. Because otherwise we will have this aliasing issue where a continuous sinusoid will be mapped, many continuous sinusoids will be mapped onto the same discrete sinusoid, as we discussed when we proved the sampling theorem in 1D. Recovery happens by taking inner products with the corresponding discrete sinusoid, inner products of the samples, of this matrix of samples that we saw before. We can express this inner product, so this is this square here, and we have this outer product of the two 1D sinusoids. So this inner product is exactly the same as writing so having these two products like that. Okay, so the inner product between these two things is exactly equivalent to just taking the vector times the matrix here times the other vector. Okay, this is easily shown just by basic linear algebraic manipulations. And the point is that we will recover the original Fourier coefficients. How do we prove this? Essentially in the same way as we proved it is in one dimension. We have that the 2D continuous the 2D continuous sinusoids get mapped to discrete sinusoids, and if we have this condition here, each continuous sinusoid can only be mapped to one discrete sinusoid. Now we express the samples in terms of this sum of discrete sinusoids. We're taking the inner product with one of them. They're all orthogonal, so this inner product is going to be 0 except when k1 is equal to m1 and k2 is equal to m2, and boom, we end up with actually here I have to tell you I've forgotten the t over n squared. Okay, so basically again all of this is 0 except when k1 is equal to m1 and k2 is equal to m2, so we recover the original Fourier coefficients. I've gone a little bit quickly through this because the argument is essentially the same as in one dimension. We can also define an extension of the 1D DFT or discrete Fourier transform to 2 dimensions, exactly as we did in one dimension. This is just the inner product of a vector, in this case a matrix that is n by n, times the corresponding discrete sinusoid. It turns out that we can write this as this DFT matrix times the matrix times another DFT matrix, where this is the 1D DFT matrix, just because this guy again is equal to the outer product of these two 1D discrete sinusoids. It can be computed very efficiently with the FFT, because realize that this is just taking FFTs of each column, and when you are done you take FFTs of each row. So the complexity is actually only n squared log n, and realize that this guy has n squared entries. X has n squared entries, so it doesn't really get much better than that. It's super important that we have the FFT, because otherwise computing discrete Fourier Fourier transformations, like computing the DFT of images, would be extremely computationally intensive. In MRI, for example, that would be a deal breaker. It's absolutely crucial that we have the FFT. When we want to take the inverse FFT, we can show that, again, we just apply inverse FFTs to the columns and rows of the matrix, and it inverts the 2D DFT. This is easy to show. Okay, so what have we learned? We have learned the properties of multidimensional sinusoids, which are these planar waves that have a vector valued frequency. We have defined the multidimensional Fourier series. We have defined the multidimensional discrete Fourier transform, and we have established the sampling theorem in 2D, which follows essentially the same ideas as in one dimension. Thank you very much.